Good morning, class. Today I'd like you to start with this absolute value equation. Go ahead and pause the video and see if you can solve this independently. Okay, I'm assuming you've unpaused the video now, and now we're going to discuss it. One of the things that we have to be aware of is when we're dealing with solving an absolute value equation like this, be very careful not to um, collect like terms or distribute things inside of the absolute value. That has unintended consequences. Remember, our whole thinking is that thing inside the absolute value could be one of two numbers, and it's easiest to see what those two numbers are if the absolute value portion is isolated. So the first thing I would do with both sides of this is to just add 6. So this is going to become 5 times the absolute value of 2x plus 3 will equal 29 plus 6 should be 35. And now that we've got the 6 added to both sides, the next thing I'm going to do is I'm going to divide both sides by the number 5. And when I do that, I'm going to get the absolute value of 2x plus 3 equals the number 7. So we are now at a point where we can look inside and we can remind ourselves that this thing inside is either a positive 7 or it's a negative 7, right? There are two values that 2x plus 3 could be that would produce an answer of 7 when it's trapped inside the absolute value, either positive or negative 7. I typically do the negative portion first, so I will write that 2x plus 3 could be negative 7, or, and by the way, within an equality, it's always going to be an or that joins them, or that number inside could have been positive 7. So, or 2x plus 3 could be the number 7. And to solve these, we're going to do the same two steps on both of them, right? We're going to take away 3, so this is going to become 2x equals negative 10. Therefore, x is negative 5, or 2x equals 4. Therefore, x equals the number 2. So my solution is that x could be either negative 5, or it could be 2. And it's always worthwhile to come back in and plug that in. So I'm just going to put in this value of x here. So if I look at 5 times the absolute value of 2 times negative 5 plus 3, and then I'm going to, subtract 6 from that. And the question is, what does that become? Well, this is going to become the number negative 10, and negative 10 plus 3 is going to be a negative 7. Negative 7 times 5 is negative 35. And if I take the absolute value of negative 35, that becomes 35. So this becomes 35 minus 6, which is indeed 29. So when I plug in negative 5, we can see it checks. If I plug the positive 2 in, let's verify that that works as well. So if instead of being a 5 right there, this was the number 2, this is going to become 5 times the absolute value of 4 plus 3. The absolute value of 4 plus 3 is the number 7. So this is going to become 5 times 7, which is positive 35. And 35 minus 6 is also 29. So the values of negative 2 and the value of positive 2 and the value negative 5, both are solutions to this absolute value inequality. Yesterday we looked at graphing linear inequalities in which we had two variables, and I just want to point out that we're not restricted to just lines. We could have, here's an exponential inequality with both x and y, and if I was going to attempt to graph this manually, I would probably want a small table of values. So I would consider whoops, go back, go back, go back. I would consider I would definitely look at what x when x is 0, and I can see if x is 0, then the 0.8 to the 0 power is going to become 1, so that'll just produce 3. If x is the number 1, I'm going to have 0.8 times 3, which would give me 2.4. If x is 2, I'm looking at 1.92, and I'm glancing at these on my calculator. If x was 3, I'd be at 3 rather, I'd be at 1.57. So again, the thinking here is I keep multiplying by 0.8, so as every single time I move forward, 80% of what I have remains. And at the 0th term there, I've got 100% of that original 3. I can also go backwards one. If x was negative 1, I would hit negative 1 would give me 3.75. And I could actually go back and look at negative 2 also. Negative 2 would give me 4.68. So enough values now. Now we can go ahead and graph this. So at 3, or when x is 0, we're at 3. When x is at 1, we're at 2.4. So right below 2.5. When x is at 3, or 2 rather, no, I'm sorry. When x is at 1, we're at 2.4. There we go. When x is at 2, we're at 1.92, just below the number 2. When x is 3, we're just a little bit above 1.5. And this pattern just continues, right? The x-axis is going to act as an asymptote. If I move back to the negative 1, I'm at 3.75. So at negative 1, I'm getting close to 4. At negative 2, I'm at 4.68, so I'm getting close to 5. I feel like I need to look at some more. At negative 3, I'm at 5 point, I'm going to round to 5.9, so almost 6. At negative 5, I'm at 9. Okay, at, no, at negative 4, I'm at 7.32. 7.32. Anyways, so we get kind of a rough idea what's happening now. Because this is strictly less than, right, I'm looking at a dashed boundary line. So my boundary line is not going to be solid, meaning that the points on this line are not included as part of the solution. This is just separating the Cartesian coordinate plane into two different regions, this region and this region down here. Now, when I plug in 0, 0, right, if I want to test a point to see if I'm shading above or below, I end up getting y is 0, so I'd say 0 is greater than 3, which is clearly false. Because this is false, right, 0, 0 is not a solution, so that means I'm left with the values above. And literally, if you look at this, the way that we're reading this from left to right, it says we want y values that are greater than the curve. So you've got to be careful and make sure that it's written the right way and you're interpreting it, but that is clearly what it's saying. We're graphing the y values that are greater than the boundary, so it's the things that are above that boundary. And of course, even though we're not in the classroom, our friend Desmos is always there with us, so I could come over and I could look at that graph here rather quickly. So this is just 3 is greater than, oh, not 3, y is greater than 3, and then multiplied by, I'll put 0.8 in parentheses raised to the x power. And you can see this graph right here. That's what we were talking about. So when every single time I add one of those to the Cartesian coordinate plane, what I'm doing is I'm adding a constraint. So if I have a physical situation that's being described, this equation constrains where I would look for my answers, right? So solutions live in this region, not in the region below. And sometimes we can add multiple constraints, and I want to look at a couple different ones individually, but let's look at this constraint. Let's consider y is less than 4 times 1.15 raised to the... Now, interesting. So if you look at this, we're starting at 4, so I know we're going to begin here, but because my multiplier is greater than the number 1, I know that this is going to be growing. In fact, this is going to show growth of 15% each time x increases by 1. This shows a decrease of 20%. So I know that we're multiplying by zero point 0.8, but this means 80% of what I had remains, so therefore 20% is going away. So if I hit to the x power, you can see there's growth, right? Now if I look at these two together, right, the solution region is now clearly not here. This is a region that satisfies only the top graph, and this is a region that satisfies only the bottom graph. This is a region, right, that satisfies both. So we're looking at two constraints at once here. A couple other constraints that might make you say, huh, what about y is greater than or equal to the number 3? And that's literally it. I'm not putting an x there. I'm just going to say y's are greater than or equal to 3. Well, I want you to notice what's happening here. This is the line where y equals 3, right? Y is equal to 3. X is changing as my cursor moves along, but y's are always 3. And notice that it's a solid boundary, right? Because I've got the or equal to, so it's including this, and it's everything above that. So this is y's are greater than or equal to 3. And then I'm going to put another constraint that I want you to be aware of. Let's look at this constraint. Let's look at x's are less than the number 2. So this one, you can see it is a dashed line now, meaning that obviously this is not included. This line is the line x is 2. Every single point I stop on here, the x value is 2. Here y is 1, y is 2, y is 3. Clearly y values are changing, but x is held constant at 2. And it doesn't include the boundary. Now, if I'm looking at a fairly complex situation, I could have a lot of different constraints. And when I look at all those constraints together, right, it's a little hard to see here, but there's a very small region that satisfies all of those constraints. And the region is, I actually kind of lost track of, okay, so this region, yeah. So this region right here satisfies those two. As soon as I say x has to be less than 2, it's not a triangular region because it's bound by some curves, but this is the region that satisfies all three. And then I'll put one more in, y's have to be greater than or equal to 3. So now you can see it's this region that it's got this straight line, and then it's got a right angle, and then this dotted curve, and then this, a dotted line rather, and then this curve, and then this curve. So this region right here contains xy pairs that satisfy all of these constraints that we're looking at. Another thing I'd like for us to consider is if we're given a graph, we can say, okay, what's the constraint that's specifying that that shaded region is where solutions are as opposed to the region above it. So on this, if I was to think about the boundary line, right, the equation of that boundary line would be y. Oops, why does that? There we go. That boundary line would be y's are equal to something. So I'm not thinking about the inequality yet, just the boundary. The slope of this appears to be starting here. I go down 1 unit, and then I go over 1, 2, 3 units, and I land at another point. So my slope is negative 1/3 x. So every single time x increases by 1, I go down a third, down a third. And I'm beginning at negative 1. My y-intercept is at negative 1. So y equals negative 1/3 x minus 1 is my boundary. The boundary is not included, and I'm selecting out, right? This graph is selecting out those points that are clearly below this curve. So my inequality here, our y values, are those things that are less than, strictly less than, not including the curve negative 1/3 x minus 1. So if we have a graph, we should be able to identify the constraint that selected out these as working solutions as opposed to the other side where the solutions do not work. Okay, so this is a problem that I'd like for you to do on your own, and you're going to see this set up inside of that. Well, you're looking at it now because this is the doc I'm handing out. Um, and what I'm looking for is for you to identify all the countries that should receive aid, right? What are the countries that should receive aid? So these should be the names of countries. And then I also want you to include the graph, right? A screenshot of the graph that you produced in Desmos. So make sure you click in this box and you Control V or paste into this box the graph and resize it so it fits fairly nicely. One of the purposes, in theory, of the United Nations is to have nations work together to help each other. Recently, the members of the UN decided to give grants to poor countries to help reduce poverty. However, the United Nations only has the resources to help those countries with the greatest need. Therefore, it was decided that only countries in which the number of people in poverty is more than one half of its total population would receive foreign aid. Okay, so those words right there, you can see I bold them again. So that's clearly talking about a constraint. I want you to look at the graph and add that constraint to the graph in Desmos, and then give me a report back on what you're seeing there. Okay, so finally, this will be the document you see. I'm just going to be pasting the video right here, so you'll see the video here. This is the stuff. You'll click this link, and it'll take you to the Desmos, and you'll type your response in these boxes. Below it says photo of your homework, 9-58 through 9-64. And then below that, on a third page, you've seen me posting homework solutions every day. So those will be below here on a third page for you to use. And finally, I just want to say that as you're doing your work for this class, really spend some time to make sure you understand very, very clearly how to do these problems. I know from a lot of experience that my solution is not the only solution, but if you're not getting these answers and there's even the slightest amount of ambiguity, please take the time to watch the video solutions. I consider that part of your assignment. Occasionally, if you watch these, I take the point of view that I'm trying to be thorough in my explanations, but I think if you don't watch a few of them, you're going to be missing some input because a lot of times if you're in class and you ask the questions or someone else asks the question, you're going to hear me talk about it and have the opportunity to clarify maybe some misconceptions you have. So do make sure that you're checking your answers and that you are watching the linked videos when appropriate. All right, that's it for today, class. I hope you have a good day, and I look forward to seeing you again soon.